Hello, and welcome to today's webinar, The Path to Resilient GNSS Anti-Jamming Solutions from Antenna to Receiver, brought to you by GPS World Magazine and our sponsor of the event, Calian. I'm Hallie from North Coast Media, the content marketing manager for GPS World Magazine, and I will be your event manager for today's presentation. At this time, I'd like to get you comfortable with our council and the ways you can participate during today's presentation. Please notice the Q&A panel on the left-hand side of your console. If you have a question, type it in the panel's text box, then click Submit to place your question in queue. We encourage you to ask and enter any questions you may have for our speaker during the presentation. We will address these questions at the end of the presentation during the Q&A portion. Questions submitted during registration have already gone to our speaker and may be covered during our presentation. If you experience any technical difficulties during today's event, you may use the same Q&A panel on your screen to submit your issue, and technical support specialist Jesse or I will personally assist you. Finally, you may learn more about today's speakers by viewing their bio, photo, and contact information in the panel located in the upper left-hand corner of your console. Now I'd like to introduce today's speakers. Today we will be hearing from Heidi El-Gamraoui. Dr. Heidi is an assistant professor at the Electrical and Computer Engineering Department, Royal Military College of Canada, and the Deputy Director of the Navigation and Instrumentation Research Lab. Dr. Heidi holds a Bachelor of Science degree in Electronics and Communications Engineering and a Master of Science degree in Engineering Mathematics and Physics, both from Cairo University, Egypt. In addition, she holds a PhD degree in Electrical and Computer Engineering from Queen's University in Canada. Mohammed Imara. Dr. Mohammed Imara is a senior RF engineer at Calian GNSS, where he develops antenna and RF front-end solutions for GNSS systems. He received a Bachelor of Engineering degree in Aerospace Engineering and Master of Applied Science and PhD degrees in Electrical and Computer Engineering from Carleton University, Ottawa, Ontario, Canada, in 2016, 2018, and 2023, respectively. And lastly, Jean-Marie Sleewagen. J.M. Sleewagen is lead architect at Septentrio, Belgium. He is responsible for GNSS signal processing, system design, and technology development since the company's inception in 1999. He received his Master of Science degree and PhD in Electrical Engineering from the Free University of Brussels. He is the inventor of multiple patents in the field of GNSS signal processing. He received the Institute of Navigation Burka Award in 1999 and the GPS World Products Leadership Award in 2018. At this time, I will turn the presentation over to Heidi. Take it away.
Thanks so much, Haley, for the introduction. Good afternoon, everyone, and welcome to today's webinar. I'm so glad to have you all here and to present on a topic that I'm truly passionate about, which is jamming. And I hope you will find today's webinar both informative and enjoyable, so let's dive in. So before we dive deeper, let's first discuss why GNSS signals are vulnerable to interference. GNSS signals travel a very, very long distance from satellites orbiting around 20,000 kilometers above the Earth. By the time they reach the receiver on the ground, they are incredibly weak, often below the noise floor, and that makes them highly vulnerable to interference, whether it was intentional or unintentional. So basically, any radio frequency signal in band with the GNSS could potentially cause interference. And most critically, GNSS signals could be intentionally jammed or smoothed, posing significant errors to navigation, positioning, and timing application. Understanding these vulnerabilities are crucial as they directly impact the reliability of GNSS-based systems. So first, let's differentiate between two major types of intentional interference, jamming and spoofing. Jamming occurs when a radio frequency signal is transmitted with sufficient power on the same frequency bands as GNSS, overwhelming the receiver and preventing it from acquiring or tracking the satellites. So essentially, it acts like a signal blocker, rendering GNSS-based positioning and timing unavailable. Spoofing, on the other hand, is more sophisticated. Instead of just blocking the signal, spoofer transmits a fake GNSS signals that mimic the real ones, misleading the receiver into calculating an incorrect position, velocity, and time. And this can have serious consequences, as it can cause the system to unknowingly rely on false information, leading to navigation errors. I'm here showing a figure to better explain spoofing. So this is one of the spoofing experiments that I have attended in Jammer Test 2023. The antenna and the receiver were static and located at the blue circle in the figure that you see before you. So while the computed position by the receiver is the red trajectory that you could see, so the receiver was following the spoofing trajectory that was transmitted at that time. So generally speaking, jamming signals can fall into two main categories, narrowband and wideband. Narrowband jamming is concentrated over a small portion of the GNSS frequency spectrum. It typically manifests as a single tone or multiple tone signal with a narrowband frequency range. And since it affects only a limited part of the GNSS bandwidth, receiver with adaptive filtering or notch filtering techniques can sometimes mitigate its effects. However, depending on the power of the jammer, even narrowband interference can severely impact the signal tracking and degrade the performance. On the other hand, wideband interference spreads across a broader range of frequencies, covering a significant portion of the GNSS spectrum. And this type of jamming is more disruptive because it impacts multiple GNSS signals simultaneously, making traditional filtering techniques less effective, which is why wideband jamming is better addressed at the antenna level using CRPA techniques. So wideband jamming can be generated using, for example, noise-like signals, and it can severely degrade GNSS receiver performance, leading to complete signal loss. It is very important to note here that understanding the spectral characteristics is very essential for developing effective mitigation strategies for the jamming. I'm here showing two of the most commonly used signal types for jamming GNSS, which is continuous wave, which is basically a single tone that does not change its frequency over time. And the chirp signal, so the chirp signal, it changes its frequency. It could be linearly, as you could see here from the spectrogram, or it could change its frequency quadratically or even with higher orders. There are various other types that could be used to jam GNSS. So amplitude modulation jamming signal varies its amplitude of the jamming signal over time. So this type of interference is less common used in GNSS jamming, but still can degrade the receiver performance. The frequency modulated jamming, it changes the frequency of the jamming signal within a certain range, and that creates kind of a sweeping effect across the GNSS frequency band, which could be narrowband, wideband, and that makes it difficult for the receiver to filter out the interference. And it can be particularly disruptive because it impacts a broader portion of the spectrum over time. The noise jamming is one of the most effective forms of interference against GNSS. It involves transmitting random noise-like signals, either narrowband or wideband. And wideband noise jamming in particular can completely overwhelm GNSS signals, leading to total loss of positioning and timing capabilities. And that type of jamming is difficult to mitigate at the receiver level, so it's better addressed at the CRPA or the antenna level because it resembles natural noise, but at a much higher level. So now that we have discussed different types of jamming signals, let's examine their effect on a GNSS receiver. The impact of jamming can vary in severity, ranging from minor disruptions to a total complete loss of the service. So one of the things that could happen, loss of lock to one or more satellites, which happens at lower interference level, where GNSS receiver may initially struggle to track certain satellites. And this happens when the jamming signal degrades the carrier to noise ratio, making it difficult for the receiver to maintain a stable lock. And the receiver may still function, but with reduced accuracy and reliability. Other thing that could happen when you increase the jamming power more, the receiver may lose lock to multiple satellites, reducing the number of available signals for positioning, and that will lead to degraded positioning accuracy, increased dilution of precision or DOP, and potential errors in navigation and timing. When you increase it more and more, the jamming power, the receiver may no longer be able to acquire or track any satellites. At this stage, GNSS-based positioning and timing functions fail entirely, and the receiver will be in a complete outage, which can have severe consequences for critical applications such as aviation, maritime navigation, and military operations. So I'm showing here the jammer centered at the red circle. And red is always bad, where the receiver experiences complete outage. Then the yellow circle, where the receiver is struggling to keep lock to satellites due to jamming. And in this area where you could experience some positioning errors. And then the green circle, which is the safe zone. And you could imagine the radii of the red and yellow circles expanding or shrinking based on many parameters, such as the jamming power, the receiver sensitivity. Do you have any implemented signal processing techniques inside the receiver that mitigate jamming, or are you using CRPA antennas or not? So one of the biggest challenges with GNSS jamming today is how easily accessible jamming devices have become. Despite being illegal in many countries, with just few clicks, anyone could purchase a low-cost jammer online, often disguised as a signal blocker or privacy device. And these devices, originally marketed for personal uses, can cause widespread unintentional disruptions, affecting not only the person that is using them, but also nearby critical systems. Even small, low-power jammers can interfere with GNSS reception over a significant area, leading to navigation failures, time disruptions, and safety risks as well. The fact that these devices are so readily available highlights the urgent need for better enforcement, interference detection, and mitigation strategies to protect GNSS-dependent applications. Beyond the availability of these illegal jamming devices, what makes GNSS jamming even more concerning is that it does not require purchasing a dedicated jammer at all. With the rise of the software-defined radios that are widely available, configurable, and completely legal for many legitimate applications, GNSS jamming has become even more accessible to those with basic technical knowledge. Unlike traditional jamming devices, SDRs allow users to transmit customized signals simply by programming them through open source software. With the right scripts and minimal hardware investment, even an entry-level SDR can generate interference that disrupts GNSS reception over a considerable area. This ease of access poses a significant challenge because SDR are intended for research, education, and legitimate communication purposes, yet they can be misused for GNSS jamming. So what you are looking at here is a live map of GNSS jamming incidents worldwide. This visualization makes it clear that GNSS interference is not just an isolated issue. It has become a widespread challenge, particularly in regions experiencing geopolitical conflicts. One of the observations is that many of these jamming incidents are concentrated in conflict zones where GNSS disruption is being used as an electronic warfare tactic. By denying access to accurate positioning and timing, military forces can disrupt navigation, surveillance, and communication system impacts both military and civilian infrastructure. However, the consequences really extend beyond the battlefield. Commercial aircraft, maritime navigation, and even financial institutions and networks relying on GNSS timing can be affected. So, as I mentioned, while jamming is often associated with military operations, its impact extends far beyond the battlefield. So civilian sectors also experience serious disruptions due to intentional and unintentional jamming. I'm here listing 3 of the recent incidents, but if you Google jamming incidents or civilian impacts on from jamming incidents, you will find plenty of them. So now that we have seen the growing impact of GNSS jamming, the key question is, what do we do about it? Addressing GNSS interference really requires a structured approach, which is often categorized into 3 main key areas: the electronic support, electronic attack, and electronic protection. Electronic support involves monitoring or analyzing the radio frequency environment, so basically RF situational awareness, to detect and locate sources of GNSS interference. That could include spectrum monitoring, interference localization, and signal classification to distinguish between unintentional interference and deliberate jamming. The goal is to understand the threat and take appropriate countermeasures before the significant disruptions could occur. And then electronic attack, it refers to the offensive measures designed to suppress jamming threats. And that could involve jamming the jammer, deploying directional countermeasures, or even targeting adversary electronic warfare assets to restore GNSS functionality in critical areas. And then comes the electronic protection, which focuses on making GNSS more resilient, which is all that webinar is all about. So making GNSS systems more resilient against interference and that jamming. And that includes techniques like adaptive filtering, the use of multiple antennas, CRPAs, advanced signal processing techniques implemented inside the receiver to countermeasure the interference coming from hostile signals. By combining these three elements, electronic support for RF situational awareness, electronic attack for response, and electronic protection for resilience, we can develop a comprehensive strategy to safeguard GNSS reliant systems. Our first line and most important line of defense against GNSS jamming is the spatial filtering, which leverages null steering and beamforming techniques to reject interference while maintaining access to valid GNSS signals using multiple antenna arrays. And this is going to be covered in much more details in the next presentation. So anti-jamming techniques can also occur at the pre-correlation levels. It can occur at the time domain, frequency domain, or transformed domain. At the time domain, the most common used technique is the pulse blanking, which is used for pulsed interference signal. At the frequency domain, using notch filtering specifically for mitigating continuous wave signals, or cascaded notch filtering if you have multiple continuous wave signals. And in transform domain, you could use something like multi-resolution analysis using wavelet packet transformation, where you decompose your signal into multiple subbands, and you detect which subbands are affected by interference and deal with those to filter out the effect of interference. At the post-correlation levels, there are other things that could be used to mitigate interference. So the tracking domain, so at the tracking domain, instead of using the conventional scalar tracking, you could use the vector tracking, which is more robust to interference. At the negation domain, you could use smoothing or adaptive filtering techniques to smooth out the errors that could happen in the position due to the presence of jamming. And of course, you could always benefit from any external sensors that you have on board of the platform that is being attacked by a jammer. The most commonly used one is the INS. You could integrate GNSS with INS in loosely coupled fashion, tightly coupled, or ultra tightly coupled. And not only INS, you could use any sensor on board, LiDAR, radar, vision, so any other sensor that you could benefit to bridge that GNSS outage due to jamming. On top of all those jamming mitigation techniques, the use of multi-constellation could also be seen as a potential solution to jamming, as you could always use GNSS signals that are less affected by jamming to maintain your position, navigation, timing information. The growing threats of GNSS jamming in recent years really highlights the importance of implementing and deploying those techniques for resilient navigation. However, this brings us to the questions. Are these techniques enough? And I will leave that as an open question for the audience. As we move forward in today's webinar, you will hear from other presenters who will delve deeper into jamming mitigation approaches. After learning about the solutions, I encourage you to reflect back on this question and think about whether the current strategies are sufficient or if we need to go even further. With that, I will hand it over to Muhammad.
Thank you, Heidi, and hello, everyone. We will now discuss how to make a GNSS system more resilient to jamming. And we start with the GNSS antenna, which is the first component to process the satellite signals. So if the antenna saturates due to jamming or interference, or if the antenna allows too much power to enter the system, then the receiver cannot correct the resulting signal degradation, and it may not be able to perform its own anti-jam functionalities. What it means is that the antenna is the first line of defense against interference, and so the choice and the installation of the antenna are both very critical to the overall system performance. And the focus of this part of the webinar will be on the active GNSS antenna, which is the interface between the GNSS signal and the GNSS receiver. It consists of two main parts. First, a passive radiating element, such as a patch, a helical, or a cross dipole, and then an active RF circuit that consists of an arrangement of filters and amplifiers that condition the signal before sending it to the receiver. The antenna should also include protection from electrostatic discharge, and in some cases may include lightning and surge protection. Let us now see what the active antenna can do to help the receiver calculate the most accurate PBT solution. So the role of the active antenna is to receive and preserve the quality of the GNSS signal. And it does that by amplifying the signal to a suitable power level that the receiver can work with. And in the process of amplification, the antenna also defines the noise figure of the system, which has a direct impact on the satellite carrier to noise ratios. Lastly, and more relevant to this discussion, is the role of the antenna in protecting the system from interference. And this interference can be from factors external to the system, like Heidi mentioned, but they can also be from the way the antenna is integrated within the rest of the system electronics. And each component in the antenna can play a role in protecting the receiver. And I'm going to discuss four main techniques. The first is spatial filtering, which is implemented in the radiating element component of the antenna. And then frequency filtering, band isolation, and high linearity, which are techniques used in the RF circuit design of the active antenna. We will start with spatial filtering, which makes use of the antenna radiation pattern. And the radiation pattern is a parameter that defines the sensitivity of the antenna to signals arriving from different directions. So what you see here is an example of a radiation pattern showing gain versus elevation. And typically, the antenna would have high gain or high sensitivity at zenith, and then the gain would reduce as you go from zenith to horizon. Now, the idea is if we can control the radiation pattern, we can shape it in such a way as to make the antenna more or less sensitive to signals arriving from different directions. So for example, if we know that there is a jammer at horizon from one direction, we can direct a null or an area of low sensitivity towards that jammer. So what this means is that we're using the antenna pattern as a spatial filter to attenuate in-band jamming from one direction while still receiving the in-band desired signals from other directions. And in GNSS, there are two main techniques to achieve this radiation pattern customization. The first is based on fixed radiation patterns, and that makes fixed radiation pattern antennas, or FRPAs. And the second is based on adaptive or dynamic radiation patterns, and that makes controlled radiation pattern antennas, or SERPAs. FRPAs make use of the knowledge that most jamming arrives at angles of low elevation with respect to the antenna. So with that in mind, we designed the TW3742AJ, which is a single band L1 solution that is based on a patch antenna and 4 directors that enhances the gain of the antenna at zenith and creates an azimuth null at a low elevation angle all around the antenna. So with this design, we can achieve jammer mitigation with up to 30 dB of null depth. And we define the null depth as the difference in the gain between a standalone element, in this case, a single patch antenna, and the gain of the FRPA configuration in the direction of the null. And to give you an idea of what these numbers mean, 20 dB of attenuation can get you 10 times closer to the jammer, whereas 30 dB can get you about 30 times closer. We also developed a triple band solution called the AJ977XF. And this design is based on 2 stacked helical antennas that are separated and excited in a way that enhances the gain at zenith and creates an azimuth null all around the antenna, but now it's within the 3 main GNSS bands. And similar to before, we can achieve null depth of up to 30 dB when comparing the radiation pattern with a single helical antenna. So these protections that we get from the FERPAs come at a trade-off. And in this case, there is a risk of losing low elevation satellites. And the reason is when you form a low elevation null to mitigate in-band jamming, you're also making the antenna less sensitive to satellites arriving from these directions. So these solutions are typically not ideal for applications where you need to receive corrections over the L-band. And to give you an idea of the effect of the null on the carrier-to-noise ratios, we measured a standard patch and compared it with the TW3742AJ. And what you see here is for a standard patch, the carrier-to-noise ratios of low elevation satellites are in the mid-40s, whereas for the 3742AJ, they are in the mid to low 30s. So you lose about 10 to 15 dB in carrier-to-noise ratio when you use a FERPA. With that being said, one of our customers tested the 2 antennas in a location where there is intermittent jamming from trucks driving by. And over a span of 8 days, the standard patch lost the GNSS signal for over an hour, whereas the 3742AJ only lost it for under a minute. So in a situation where you are expected to be exposed to jamming, the decrease in the carrier-to-noise ratio is a worthwhile trade-off to ensure access to GNSS information. The second type of spatial filtering is the CRPA. And the CRPA is based on an array of antennas with a beamforming network that allows us to control the magnitude and the phase of each element. And with this control, we can create radiation patterns by generating constructive or destructive interference in different directions. So right away, you see that this provides a lot more flexibility in controlling the radiation pattern than a FERPA. So for example, with a CRPA, we can generate beams directed towards specific satellites, nulls directed towards jammers, or a combination of the two. And in CRPAs, the more antennas you have, the more degrees of freedom you have in controlling the pattern. And generally, the number of nulls is 1 less than the number of antennas. And there are 2 categories of CRPA, which are analog and digital. And these are essentially classifications based on how the signal is processed in the beamforming network. So in analog CRPAs, the beamforming is done in the analog domain. So the GNSS signal remains as an RF signal from the antenna all the way to the receiver. And with this architecture, we can achieve null forming through space adaptive processing, which makes use of the spatial diversity provided by the antenna array. And we can get null depth between 20 and 40 dB, depending on the implementation and the number of antennas used. A key advantage of analog CRPAs is their low power consumption. And the reason is the signal is received and processed in the same domain without any need for up conversion or down conversion or analog to digital conversion. And also space adaptive processing is a relatively low computational intensity calculation. One drawback of analog CRPAs is that their implementation becomes significantly more complex as you increase the number of elements. Typically, this is limited to a fewer number of elements than digital CRPAs. And at Calian, we are currently developing 2 and 4 element analog CRPAs that we expect to release in Q3. These CRPAs are lightweight and they consume very little power, that they can be powered directly from most GNSS receivers. And we also tested the 4 element CRPA with the Septentrio Mosaic X5 jammer test in Norway last year. And the system was able to function with up to 80 dB of jammer to signal ratio, which was the limit of the jammer power at our test location at that time. The next CRPA technique is the digital CRPA. And in this case, the beamforming is done in the digital domain. So when the signal is received, it's pre-filtered and amplified, then down converted to baseband and sampled to create the digital signal. And then the processing is done on that digital signal. And then the signal is converted back to RF to feed it to the receiver. In some cases, the receiver may be integrated within the digital chain. But if you want to use a commercial off-the-shelf receiver or a standalone receiver, then you need this last up conversion to RF. With digital beamforming, there are a lot more null steering techniques that are available. So in addition to space adaptive processing, we can also do space-time or space frequency processing. And these techniques offer a lot more flexibility in interference mitigation. So for example, we can more effectively null broadband jammers and can have better satellite availability. With digital SERPAs, you can also achieve null depth of up to 50 dB. Now, these advantages of the digital SERPA come at a high computational cost. So these architectures typically consume a lot of power, and they also weigh a lot more because of the heat sinks needed to dissipate the heat during operation. And because of their capabilities, digital SERPAs are also relatively more expensive. We now switch gears to techniques used in the RF design. And the first is frequency filtering, which is needed to attenuate out-of-band interference. And the best location to implement this is right at the input of the antenna. So when the signal is received, it's immediately pre-filtered to separate the upper and lower GNSS bands. And then we add multiple filtering stages after that to further enhance the out-of-band rejection. With this architecture, which we call extended filtering, we can achieve up to 80 dB of out-of-band mitigation, as you can see from this plot. The trade-off in this technique is between the filter sharpness and the noise figure. So the higher the roll-off between the in-band signal and the out-of-band signal, the higher the loss in the filter. So when we design these circuits, we have to be careful to ensure that the noise figure is as low as possible. The next technique is band isolation. And this technique aims to make the antenna more resilient to single band jamming. And we do that by separating the paths between the upper and the lower GNSS bands. So the two bands do not share any stages. So what it means is that if, for example, there is jamming on the L1 frequency that causes saturation to the L1 components, or maybe even damages any components in the L1 chain, then the L2 signal remains unaffected and the receiver can still process it and calculate the solution. With this configuration, we can achieve up to 30 dB of isolation between the upper and the lower bands, and we can combine it with the 80 dB of out-of-band rejection, and we call this technique Extended Filtering Plus or XF Plus. The drawback here is that we require more components, which makes the layout a little bit more challenging, and because we're using more active components, there's also higher power consumption in the antenna. The last technique I will discuss is high linearity. And what we aim to do here is to extend the linear operating range of the amplifiers to allow them to handle more power, either in band or out of band, before they saturate and distort the signal. And this is especially important in the last amplification stage, because that's the one that receives the most power due to the amplifier stages that come before it. And we achieve high linearity by choosing components that are designed for this purpose, and by also optimizing the bias conditions to the components that we use. Unfortunately, high linearity requires more power, so that's the drawback for this design. So to summarize, I presented 4 techniques used in the active antenna to make it more resilient to interference. Spatial filtering attenuates in-band jamming, and it's implemented in the radiating element. Frequency filtering is implemented in the RF design, and it's important in attenuating out-of-band interference. High linearity amplifiers make the system more resilient to high power jamming and interference. And finally, isolating the GNSS bands ensures that jamming on one band has minimal impact on the unjammed band. So GNSS resilience begins at the active antenna, but it doesn't stop there. Jean-Marie will now discuss resilience techniques used in the GNSS receiver.
Thank you, Mo, and hello, everyone. In this last part of the webinar, I want to dive into the receiver, and as an example, I will try to explain and give more details about the interference mitigation technique we've been implementing at Septentrio, and which we call AIM Plus technology. But before starting, let me recap the main building blocks of a GNSS receiver. So the signal starts at the antenna, it then enters the analog front end, where it's filtered, amplified, and down-converted before being digitized in the A to D converter. The A to D converter inputs the signal tracking channel where ranging measurements are computed for all the signals of all the satellites in view. Those ranging measurements in turn are used by the PVT engine to compute the position, velocity, and time. Now the question is, where does interference mitigation take place in this process? And the answer is a bit everywhere. A well-designed receiver will have an analog front end with a high linearity to avoid saturation. It will process all bands to always leave a band available in case some bands are jammed. The A to D converter must be dimensioned with multi-bits and high rate. The signal tracking channel must be able to operate on low power signals, so have high sensitivity capability, and preferably be of adaptive type, so adapt themselves to the signal condition. The PVT must be able to process any type of signals or constellation in order to fall back to something that still is not affected by interference in case a constellation or a signal would be jammed. This is called frequency and constellation diversity. On top of that, in septentrion receivers, we've added a dedicated anti-jam module, which is right after the A to D converter, and which is present in all our receivers. So that's a standard module in all our receivers. Its purpose is to clean up the signal from the A to D converter before it enters the signal tracking channels. So when I say clean up, maybe it's interesting to show what a clean signal looks like first. And this is what I try to do in this slide. So this slide shows two screenshots of the signal taken right after the A to D converter. This is a screenshot that all of our users can take because it's a part of our graphical user interface. In the left panel, we see the time domain representation, and in the right panel, the frequency domain. This is the L1 field, the L1 band. A clean GNSS signal looks like noise, so there is no specific pattern to be recognized here. This is just a noisy signal. In the frequency domain, it's mostly a flat spectrum with some bumps, as you can see, corresponding to the different GNSS bands. Any deviation from this noisy shape most of the time indicates the presence of interference. And I show here 4 typical, very common types of interferences that we see very often in our practice at Septentrio. The first one on the left is a case of self-interference. So that's a drone in this case with a camera mounted on it. And this camera, we've seen that when the camera was active, the GNSS band was affected by large peaks in the spectrum, very narrow peaks as you see here on the spectrum plot, which was really caused by the camera injecting noise into the GNSS antenna. So that's kind of co-located electronics which is causing interference. The second example is a time domain series of chirp samples. So those privacy devices, they have this kind of signature, which is clearly different than the noisy signal we expect from a clean GNSS signal. And the third example is a pulsed jamming signal. In this case, it was caused by high power switches in electronics nearby the receiver. Now, those 3 types of interferences are very common. And the good thing is that they are either non-continuous, or if they are continuous, they don't affect the whole GNSS band. So there is always a portion of the signal which is left unaffected by the jammer. And in that case, mitigation at the receiver side is very effective, or can be very effective if the receiver is properly designed. The last type of interference, and Heidi has been talking about that as well, is a more advanced military type of jammer, which is covering the whole GNSS spectrum and doing that continuously. So there is nothing from the signal left that can be used by the receiver. And in that case, as explained by Mo and Heidi, the surpass antennas are really a key to achieving correct interference mitigation. Now going a bit deeper into what the receiver can do, and I will show now what we do at Septentrio. We have a four-step approach when dealing with interference. The first step is detection of interference, followed by identification of the type of interference, and then we apply mitigation, and of course we report to users. This cycle here runs continuously on the receiver. There is no user action needed for that. It's a continuous process running in the background and on all GNSS bands. I will now explain those four steps in more details. So the detection step is a step where the receiver would scan the A to D signal in frequency and time domain and flag everything that doesn't look normal. So in this case, the three spikes here would be flagged, and all these pulses in the time domain would be flagged as well. Once this is detected, then the next step, and a very important step, is identification of the type of interference that we are dealing with. In that step, the receiver will try to characterize the interference as much as possible in terms of power, bandwidth, duty cycle, and things like that, and answer two main questions. The first question is it harmful to GNSS reception? Because luckily we live in a world where interference is ubiquitous, but most of them are not harmful. So it's really essential to be able to make a difference. If it's not harmful, of course, nothing needs to be done. If it's harmful, then the second question is, can we handle it at the receiver level? In many cases, yes, and then we apply mitigation. If not, then we report that to the user. And in the right panel here, I show an example of a criterion we use to detect that an interference is harmful. What I show here is the spectrum in red and then the interference mask in blue. This mask actually shows the level at which an interference becomes harmful to GNSS, in the sense that it degrades the reception of the GNSS signal. So we see here the three peaks in the red slightly exceed this blue line. So these are harmful interferences that need to be mitigated. And mitigation is done in our receivers using different rejectors. We have different types of anti-jam rejectors against narrowband interferences, such as those three spikes here. Notch filters are very effective because they can notch out a very narrow portion of the spectrum. And then against more complex types of interferences, such as the chirp jammer here, we need more advanced adaptive filtering, which we also have in our receiver, and which automatically detect this type of interference and mitigate it. In this slide, I show the interference before mitigation on the left, and then after anti-jam on the right, showing that indeed those anti-jam techniques are very effective in cleaning up the spectrum. The last step is reporting. A very useful feature we have, and I find it very, very, very useful for customers as well, is the ability in our receivers to visualize the A to D signal in time and frequency domain right after the A to D, where the interference is still there, but also after digital anti-jam. So we can measure and visualize the spectrum before and after the anti-jam module, which allows users to check the effectiveness of the anti-jam in the receiver. Next to that, in our rep interface, we have an interference flag in all pages showing the current status of the interference. And then we have many time plots, like this one is the carry to nose over time, where we added an interference time bar showing when interference was active and not active. So it allows to check if, for example, a carry to nose drop was caused by an interference or not. For all detected interferences, we also try to give as much detail as possible, such as the center frequency, the bandwidth, and sometimes even the power of the interference. So that gives an idea of how a receiver can deal with interference, I also wanted to give a word on the way we develop and validate our interference mitigation at Septentrio. And we base ourselves on two pillars, I would say. The first one is lab testing, and the second one is field testing. In the lab, we maintain a library of jammers that we can replay in signal generators and inject into the receiver to check the operation of the receiver under jamming. And we can do that on demand and replay that as much as we want to develop and improve the anti-jam module. This library of jammers is continuously updated from field data that we get from our customers, from our own experience, and also, very importantly, from dedicated jamming campaigns. And one of the very successful and useful jamming campaigns, we've been talking about that in the previous presentations as well, is the Norway Jammer Test, which is taking place in the north of Norway every year now. That's the third year. And this is represented here in the picture. What happens there is that they have a jammer on top of the hill here, transmitting jamming signals in the valley, and the receivers are put in the valley, and we can check in real life the effect of the interference on the receiver. So this is extremely useful for us to test our anti-jam module and to extend the library of jammers we have in our lab. Here I want to show an example of a characterization that we did. And this is for the notch filter, for example. In the lab, we do technical characterizations. You see here on the left